Welcome to Lecture 4 of Physics 506. In this lecture, we're going to be talking about coherent states. Coherent states play two very important roles. On the one hand, they can be used to illustrate how close a quantum system can be made to look like the classical back and forth motion of a mass on a spring. On the other hand, they play a critical role in the quantization of light, with coherent states being the quantum representation of the electromagnetic fields. We're not going to be able to get into the details about that second application here, but we will develop how these states work for the simple harmonic oscillator in this lecture, and we are going to come back to looking at the quantization of the electromagnetic fields toward the end of the class. The coherent states are the connection to the classical world, and if you like, they're the most classical of the quantum mechanical states. Oftentimes people think of coherent states as a very quantum object, but I'm going to hopefully convince you by the end of the lecture that they're actually a very classical object, not a very quantum object. So there are many different ways to motivate the coherent states. Here we're going to do it as coherent states being the eigenstates of the lowering operator A. So I have a state that I'm going to label by alpha, and when A hat acts on the state alpha, it gives back alpha, a number times the state alpha. And you might be concerned that because A is not Hermitian, how can I have eigenstates? But it turns out that the A operator can have eigenstates. However, some of our familiar properties about eigenstates do not hold. First, the alpha can be complex. It need not be real. Indeed, it is often complex. And second, the eigenstates are no longer orthogonal like they are when I have eigenstates of Hermitian operators. In fact, what we will find is the set of coherent states are actually overcomplete, and we're going to describe that in a bit more detail below. But first, we want to refresh our memories about the lowering operator A hat. So the commutator of the Hamiltonian with A hat can be written as h bar omega 0, since that's a number, I can pull it out, times the commutator of A dagger A plus a half with A. And now the lowering operator commutes with a half, and I can use the Leibniz rule to calculate the commutator of A dagger A with A, and I find it's going to be equal to minus h bar omega 0 times A hat. And similarly, if I calculate the commutator of the Hamiltonian with A dagger, I'll get h bar omega times A dagger. And this, of course, follows because the commutator of A with A dagger is equal to 1, which is a result we worked out in a previous lecture. So these lead us to conclude that the A operator lowers the energy of an energy eigenstate by h bar omega 0, while the A dagger operator raises it by h bar omega 0. And this is something that you've probably seen in previous quantum mechanics classes. I did not go over that when I introduced harmonic oscillator in the last lecture, but this is something that you've probably seen before and you should know. Now, we also know that if I look at the commutator of A with A dagger to the nth power, I will get n times A dagger to the n minus first power. And similarly with the commutator of A dagger with A to the n, except there's a minus sign, this looks in many respects like differentiation. And you can kind of think of it like differentiation and maybe even remember these commutation relations by thinking in terms of differentiation. But to derive them, you really need to use induction. And if you have not seen this before, I do encourage you to pause the video and take a moment to prove it by induction. The base case of the induction is that comes from the fact that the commutator of A with A dagger is equal to 1. All right, now what we're going to do is we're going to show what happens when the lowering operator acts on the state n. So I plug in what the definition of the state n is. It's just A dagger raised to the nth power divided by the square root of n factorial. Now I use an add 0 trick to add the term minus A dagger to the n times A hat, because A hat acting on the ground state equals 0. So I'm just adding 0 when I add that term. That then becomes a commutator, and then we just evaluated what the commutator was. It was n times A dagger to the n minus 1. If I write that n as square root of n times square root of n, you see the square root of n factorial would become square root of n minus 1 factorial. I'll still be left with a square root of n term out in front, and you find this is equal to square root of n times the state n minus 1. And similarly, you can work out that A dagger acting on the state n is equal to the square root of n plus 1 times the state n plus 1. This last proof is much easier. It doesn't require a commutator. It just requires the definition of what the state n is in terms of A dagger and recognizing that there's a 1 over square root n factorial as a normalization factor. All right, so let's now find what this state alpha is. We're going to find it by looking at an expansion in terms of energy eigenstates and then just forcing it to be an eigenstate. So we're going to let alpha equal the sum n equals 0 to infinity of Cn times n. The Cn's are just numbers. And it's always possible to write the coherent state in terms of this expansion because the set of energy eigenstates is a complete set because it's the set of eigenvalues of the Hamiltonian for the simple harmonic oscillator. So now we just let the A operator act on this state. It's going to be the A operator acting on the n state. We just worked out what that was. It's the square root of n times the state n minus 1. And we can include n equals 0 in that summation if we want, because when n equals 0, the prefactor in front is equal to 0. But we also can drop that and set that summation to go from 1 to infinity because the term with n equals 0 doesn't appear. And then what we do is we let n go to n plus 1. That restores our summation to go from n equals 0 to infinity. I have to replace n goes to n plus 1 everywhere in the summand. So I got to see n plus 1 square root of n plus 1 times the state n. And that's the form that I want to write this equation. For that to be an eigenstate, it must equal alpha times the original state. So we learn that Cn plus 1 times the square root of n plus 1 must equal alpha times Cn. Or I can rewrite that as Cn plus 1 equals alpha over square root of n plus 1 times Cn. And what we do is we start from C0. Then C1 is equal to alpha over square root of 1 times C0. C2 is equal to alpha over square root of 2 times C1, which becomes alpha squared over the square root of 2 times 1. And then C3 is alpha cubed over the square root of 3 times 2 times 1. I hope you see the pattern that is developing here. We find that Cn is equal to alpha to the n over the square root of n factorial times C0, and C0 will be determined by normalization. So that then has determined the coefficients for the expansion of the coherent state in terms of the energy eigenstates. Now, using this expansion, we can then determine the overlap of the states beta with alpha. So I just take the bra beta and multiply it by the ket alpha and use the expansion in terms of the energy eigenstates for both of them. And we are denoting C0 of alpha, what that coefficient C0 of alpha is, since we haven't determined what that is yet. And then I'll have the complex conjugate of it as C0 of beta appearing on the left-hand side. Now, using the fact that everything in those summations are just numbers except for the overlap of the state n with m, and because they're energy eigenstates, that just gives me delta nm. I can get rid of one of the summations, and then what you can see is we have an exponential there. It's an exponential of beta star times alpha, so I get e to the beta star alpha times C0 star of beta times C0 of alpha. Now what we're going to do is we're going to set alpha equals beta. That then gives me the overlap of alpha with itself. It becomes e to the mod alpha squared times C0 of alpha squared. And I just want that to equal 1. So I'm going to then pick C0 of alpha to be e to the minus 1/2 mod alpha squared. And because we pick C0 to be real and positive, we just make C0 equal to e to the minus 1/2 mod alpha squared. And there we have our expansion. Alpha is equal to the sum n equals 0 to infinity, alpha to the n divided by the square root of n factorial times e to the minus 1/2 mod alpha squared, multiplied by the state n, and then summed over n equals 0 to infinity. And then we find that the overlap between the states alpha and beta are given by e to the beta star alpha minus 1/2 mod alpha squared minus 1/2 mod beta squared. And you can see that if alpha does not equal beta, these two terms, they overlap. Their inner product is not 0. But if the difference between alpha and beta becomes large, you see that that overlap can be made as small as you would like. All right, so we just worked out eigenstates for the lowering operator. You should think about why the raising operator has no eigenstates. If you can't figure out why the raising operator has no eigenstates, you should ask me during the time that we have together on the Zoom part of the class in order to get a better understanding of why the A dagger operator has no eigenstates and the A operator does have eigenstates. All right. Now let's play around with this representation of the coherent state. We have this explicit form that is the sum n equals 0 to infinity, alpha to the n over square root of n factorial, e to the minus 1/2 mod alpha squared times the state n. I can look at the definition of what the n state is in terms of operators acting on the ground state. I'll get an a dagger to the n over square root of n factorial. You see those square root of n factorials combine to give me an n factorial. And if I group together the powers, I'll get alpha a dagger raised to the nth power. That now is just the expansion of an exponential. So I can write it as e to the minus 1/2 mod alpha squared times e to the alpha a dagger. But we're going to do even more than that. We're going to recall that e to the minus alpha star a hat acting on the ground state is just equal to the ground state, because if I expand that exponential in a power series of a, every term except the 0th term will annihilate against the ground state. So that exponential operator acting on the ground state is just replaced by 1 acting on the ground state. Now, I'm picking minus alpha star times a because ultimately I'm going to want to form a unitary operator. And the exponential of an anti-Hermitian operator, or the exponential of an operator whose Hermitian conjugate is the negative of the operator, is a unitary operator. We typically write it as e to the I times a Hermitian operator. And you're going to see why choosing e to the minus alpha star times a is going to create a unitary operator for us when the calculation is finished. It requires just a little bit of forward thinking to see that that's the case, but now we're going to substitute that in. So I now have the coherent state alpha is e to the minus 1/2 mod alpha squared, e to the alpha a dagger, e to the minus alpha star a. I'm now going to use BCH to put those two operators that are now products, e to the a operator, e to the b operator. I'm going to write them as e to the a plus b plus a correction term due to the fact that the big A operator and big B operator do not commute. And you find that when you do that, you'll get e to the alpha a dagger minus alpha star a plus 1/2 mod alpha squared. That plus 1/2 mod alpha squared will cancel with a minus 1/2 mod alpha squared. And we find that the coherent state can also be written as the exponential of alpha times a dagger minus alpha star times a. That is a unitary operator acting on the ground state. We define that as the displacement operator that we call d of alpha. And so you can think of the coherent state as the displacement operator acting on the ground state. Why do we call it the displacement operator? I'm going to show you in just a moment that it corresponds to a translation both of position and of momentum, and that's why it's called a generalized displacement operator. To do that, we have to recall our definition of the raising and lowering operators in terms of the position and momentum operators. I've written that out for you here. I'm not going to read it out for you on the tape, but you see it right here in front of you on this line. And now if I just take that definition of a dagger, multiply it by alpha, and then subtract alpha star times a, I then have to collect some terms, and when all the dust settles, what we find is that it is equal to I times the square root of 2m omega 0 over h bar times the imaginary part of alpha times x hat minus I times the square root of 2 over h bar m omega 0 times the real part of alpha times p hat. So what that says is if alpha is real, this combination is going to give me minus I x0 p hat over h bar. If it is imaginary, it's going to give me e to the I p0 x hat over h bar. And you can see exponentials of either of those terms correspond to the position translation or the momentum translation. And that means this displacement operator gives both a translation in position and a translation in momentum to the ground state energy eigenfunction. So you can think of it as shifting the eigenfunction in phase space, if that's something that you find to be a useful way of representing that. Let's think about how we do calculations with coherent states. It turns out they're very easy because the A operator acting on alpha is equal to alpha times the state alpha. And similarly, the A dagger operator acting on the bra alpha from the right acting to the left will give me alpha star times that coherent state bra. So now let's just calculate things like the expectation value of x. Well, we just write in what the definition of x is. It's square root of h bar over 2m omega 0. A plus A dagger. I let the A operator act to the right on the ket alpha. I let the A dagger operator act to the left on the bra. And you find that that is equal to square root of 2 h bar over m omega 0, the real part of alpha. I can similarly calculate the expectation value of x squared. You see when I square x, I'll get an h bar over 2m omega 0. And then when I FOIL out a plus a dagger quantity squared, I'll get an a squared plus a dagger plus a dagger a plus a dagger squared. And you can see every term except for the second term there is ready to be evaluated when it acts against the coherent state. To work with the a dagger term, I have to do my add 0 trick. I have to make it equal to a dagger a plus the commutator of a with a dagger. And then the commutator of a with a dagger is just equal to 1. And now it's in a form that I can immediately evaluate it, and I'll get alpha squared plus 2 mod alpha squared plus 1 plus alpha star squared. And that whole thing will be multiplied by h bar over 2m omega 0. This allows us to calculate the fluctuations in the position operator when I'm in the coherent state alpha. The square of those fluctuations is just given by expectation value of x squared minus the expectation value of x quantity squared. We just plug in what we just calculated, and you see alpha squared will cancel with minus alpha squared, 2 mod alpha squared will cancel with minus 2 mod alpha squared, and alpha star squared will cancel with minus alpha star squared, but I'll be left with a plus 1. And so it's just equal to h bar over 2m omega 0, and you can see it has no dependence on alpha. So this is because the coherent state shifts the ground state, but it preserves the shape of the ground state. So the fluctuations in position don't change when I'm looking at a coherent state. They're the same as what we have in the ground state of the simple harmonic oscillator. Similarly, I can calculate the uncertainty in momentum. It's a very similar calculation, except now I'm going to have an a minus a dagger, so it's going to give me the imaginary part of alpha. And I also still have that second term as the term that I can't immediately evaluate, so I have to use the commutator to write it as a dagger a plus the commutator. And you find, after all the cancellations, that you get that the fluctuations in momentum squared are given by h bar m omega 0 over 2, the exact same as what we had in the ground state. And that means that the product of the fluctuations in momentum times the fluctuations in position for the coherent state are given by h bar over 2. It's the same as the uncertainty in the ground state. All right, let's now look at time dependence of this system. We haven't discussed time dependence in general yet in the class, but one should immediately see that the time-dependent Schrodinger equation, IH bar d by dt of the ket psi is equal to the operator of the Hamiltonian acting on the ket psi, is solved by a time translation operator u of t, or time evolution operator u hat of t, that is given by e to the minus I h hat t over h bar. This always works when the Hamiltonian is time independent, and to check it, you just take the derivative. You can just immediately evaluate that derivative because h is independent of time, and there are no operator ordering issues that arise because h always commutes with itself, and you can easily verify that that satisfies the Schrodinger equation when I write psi of t in that fashion. So now let's take that operator and act it on our coherent state. Because h is equal to h bar omega 0, a dagger a plus a half, I can just pull out the 1/2 piece because that's just a number. That's going to give me an e to the minus I omega 0 t times a half. And then for the operation of e to the minus I ht on the state alpha, I'm going to put in what the definition of alpha is in terms of that single exponential, e to the alpha a dagger minus alpha star a. And now you have to think about, how do I proceed? Well, think about the operator identities that we have. This is obviously a situation where I want to move that Hamiltonian over to act on the ground state. So I want my exponential reordering, or the braiding identity, to be brought into play. I can work that out by multiplying by 1 just to the left of the ground state. I have to just make sure I get the signs right. I multiply by e to the I omega 0 t a dagger a plus a half, and then e to the minus I omega 0 t a dagger a plus a half. You see, I then have a Hadamard. That operator acting on the ground state is going to give me this factor e to the minus I omega 0 t over 2, which is the factor I told you that we can remove from the system. And now we evaluate the Hadamard. To evaluate the Hadamard, it turns out in this case it's easiest to do this by differentiation. Note that this procedure of differentiation doesn't always work, but I'm going to show you how it works here. So we have this u of t a hat u dagger of t. If I take a derivative of that object, I'm going to pull out the Hamiltonian when the derivative acts on the u operator and also when it acts on the u dagger. The sign is going to be different between the two, and that's going to give me a commutator. And because we can evaluate the commutator of a dagger a with a dagger, it's just equal to minus a. Okay, so what you see is we have calculated d by dt of this object u of t a u dagger of t, and we found it is equal to I omega 0 times u of t a u dagger of t. Now look at that. It says the derivative of this object u a u dagger is equal to I omega 0 times that object. We know that whenever the derivative of something is equal to a number times that something again, the something is just given by an exponential. And indeed, what you find then is that u of t a u dagger of t is equal to e to the I omega 0 t times the original operator a, because that's what the object is at the point in time when t is equal to 0. And similarly, we find u dagger is equal to e to the minus I omega 0 t times a dagger. And that has a sign change due to the sign change in the commutator. All right. So e to the alpha of t, which was e to the minus I h t over h bar acting on the state alpha, is going to equal the exponential of alpha e to the minus I omega 0 t a dagger minus alpha star e to the I omega 0 t a times e to the minus I omega 0 t over 2, all multiplying the ground state 0. Now notice I can now associate that phase factor e to the minus I omega 0 t or e to the plus I omega 0 t with alpha or with alpha star, and you see what we find is the state can be written as e to the minus I omega 0 t over 2 alpha e to the minus I omega 0 t. So alpha of t takes this simple form. So the coherent state evolves in time simply via the parameter alpha being multiplied by e to the minus I omega t plus a global phase that in many cases is unimportant. So this is a very simple time evolution. Now, we can use that to calculate the time dependence of position as a function of time just by looking at the sandwich alpha of t x alpha of t. We calculate what the expectation value of x is. We now just have to replace alpha goes to alpha e to the minus I omega 0 t, and that is then done for you on the second line there, where I get alpha e to the minus I omega 0 t plus alpha star e to the plus I omega 0 t. And now we just can evaluate what that is. It's the real part of alpha times cosine omega 0 t plus the imaginary part of alpha times sine omega 0 t. And then using the definition that we had for x0 and p0 in terms of real alpha and imaginary alpha, you find that that's equal to x0 cosine omega 0 t plus p0 over m omega 0 sine omega 0 t. That's what's going to come out of this when you work it out and when you let all the dust settle. All right, let's now go ahead and take a look at the expectation value of the p operator as a function of time. You do exactly the same thing, and there what you find is it's equal to minus m omega 0 x0 sine omega 0 t plus p0 cosine omega 0 t. And these two equations, I'm going to just move it down a little bit so you can see both equations. These two equations are the classical equations of motion for x of t and p of t for a classical simple harmonic oscillator that's oscillating on a spring. All right, and you're going to show on the homework exercise that the uncertainty is independent of time as well. But I want you to focus for a moment on thinking about this. This is really a remarkable result, and this is why we say that the coherent states are the most classical of the quantum mechanical states. When I look at the expectation value of position and of momentum in a coherent state as a function of time, I get exactly the classical behavior of the mass on a spring. And there's a nice visualization of this that you can see on Wikipedia. I'm going to go to the Wikipedia page and show it to you. What you see here is this is a coherent state that is evolving as a function of time. Don't worry about the phase, which is given by the colors, which I think is an awful way of representing the phase of a complex number. Just focus on the wave packet, and I want you to see that that oscillation back and forth is exactly the kind of oscillation you would expect of a particle on a spring that's oscillating back and forth. And similarly, you can see that the wave function, we're looking at the modulus squared of the wave function, but the wave function is not changing its shape as it is oscillating back and forth. And that's what the coherent state does. Unlike a wave packet in free space, which you probably did a problem on, which showed that the wave packet expanded in free space as a function of time, a coherent state in a simple harmonic oscillator potential preserves its shape as a function of time, and it simply oscillates back and forth. So that's pretty cool that that's the way that it works for a coherent state. All right, back to our theoretical development. I'm going to just summarize what we said. You can think of that the coherent states as being a blob whose uncertainty remains the same for all time as it sloshes back and forth as a classical mass, just like a classical mass does on a spring. And this is as close to a classical image that we can get with quantum systems. So the next question we're going to look at is, what are the probabilities that you can observe in the system as a function, the probabilities of different energies that you can observe when a system is prepared in a coherent state. And essentially what we're asking is how much of an energy eigenstate is in a particular coherent state. That's actually a wave function, and what we're looking at is a wave function of the energy eigenstates in terms of the coherent states, or vice versa, and we want the modulus squared of each of those components. So we just plug in our definition. So when we plug in the definition of what the coherent state is, we find that that's going to just equal the sum m equals 0 to infinity, the square root of m factorial, alpha to the m, e to the minus 1/2 alpha squared, times the overlap of the state n with the state m. That's just given by a delta nm, so we're going to, and then we have to do our squaring, so we're going to get mod alpha squared to the 2m power divided by n factorial, e to the minus alpha squared. And you also can see that if you sum that probability from n equals 0 to infinity, that total probability is equal to 1, as it must be. Now, what this implies is that for any non-zero alpha, there's always a non-zero probability to see any energy excitation. All right, now what is the maximum? What value of n corresponds to the maximum for a given alpha? To determine that, we're going to take a derivative with respect to mod alpha squared. And we find that that derivative is given by n divided by mod alpha squared minus 1 times an exponential. If we want to set that equal to 0, that means alpha squared is equal to n. So that tells me that the most likely energy eigenstate I'm going to observe is n equals square root of mod alpha when I'm in a coherent state alpha. All right, let's now move on and take a look at some additional facts about coherent states. So later in the class, in the last week, we're going to be discussing photons, and we're going to see that we can think of n as being related to the number of photons in a classical source of light. Now, most sources of light that you're familiar with are classical sources of light. This corresponds to incandescent light bulbs, and it also corresponds to lasers and LEDs. They all produce classical light. You might have thought that a laser and an LED produces quantum light, but it actually does not. A quantum light would correspond to a single photon light source, and those are available. You can actually purchase them, but they are not easy to make, and those are the only true quantum sources of light. So, in fact, if I take any of those classical light sources, light bulbs, lasers, etc., and I dim the light, it is never a single photon source. There's always the possibility of multiple photons due to an effect called photon bunching. Now, interestingly, there was an experiment that was done in the early days of quantum mechanics where they looked at a two-slit experiment, and they looked at it with light that was dimmed so low that it took 3 months to have enough light to actually expose the photographic plate and develop it into an image of the two-slit interference. And it did show a two-slit interference pattern, and it did it with what they thought was single photons going through the source at any given time, because they could estimate how many photons were in their apparatus at any given time, and it was much less than 1 at any given time as it's moving through the apparatus. So the spacing between the photons that were coming through was much larger than the time that it took a photon to go from the source to the photographic plate. Unfortunately, that's not enough to know and absolutely rule out the fact that there could be multiple photons going through the apparatus at any given time. Why was this important? They wanted to show that single photons interfere with themselves, and I don't need to have multiple photons in an apparatus at any given time to form the interference. Indeed, this actually is true, but the experiment that was done, I believe it was around 1914, did not actually establish this effect, although everyone at the time believed that it did. It's because the quantum theory was not well enough developed at that time for them to actually know that that was the case. But they actually were influenced by that and used the correct answer to develop a lot of the theory of quantum mechanics. So it's kind of an interesting thing where a blunder in the interpretation of an experiment actually led to the proper interpretation and development of quantum mechanics. It's really a very odd thing that is what happened. But indeed, that is exactly what happened with that. All right, so we've reached the end of the lecture. This is the end of Lecture 4 of Physics 506.